Today, we're delighted to welcome Anna, who's coming from us for Bordeaux in the final month of her PhD. So we're so grateful to have you with us. And she's going to teach us about this deep disco, which is, I guess, generating white matter connectivity maps from lesions, but she'll tell us more about it soon. Thanks. Over to you.
All right, thank you so much. I will hide the panel for where I can see you, so that I can see the screen actually. So thank you everybody for coming. My name is Anna. As already introduced, I'm based in Bordeaux, and I'm the PhD student of Michel Thibault-Schotten and Tomato Diaz, working on white matter connectivity or disconnectivity. And we invented this tool called the Deep-Disconnectome, which I will be introducing today. And I will be walking you first through like some background, and then we're gonna get into the hands-on like practical session where you will be able to download everything, and I will be here to answer all the questions and also help with like any installation issues we might run into, because also the toolbox is not like completely ready yet. That's why you can't find it on Git, but we're working on it. And yeah, you'll see like the preliminary stuff that should be running. It runs on my computer, it runs on like several other computers, but if you run into any issues, I'll be here to answer all the questions and help you. So yeah, let's start. I can't click. Oh yeah, so here we go. So to give you some background on like what I'm looking into, I'm doing all my research on ischemic stroke, which is a type of stroke where a clot basically gets stuck in the brain artery, and that cuts off the oxygen, leading to obviously, well, cell death, and then at some point to a lesion, right? And lesion comes obviously with impairments. So a lesion tissue basically means that you have thank you. Sorry for that. A lesion tissue means that the white matter, the gray matter, whatever is basically affected is injured, and it might cut off those white matter connections that are called white matter tracts. This, like from here, we can also look into how it impairs the functions. Since I'm sorry, there are people talking behind me. How it impairs functions, because every like white matter tract can be associated with like some sort of function, right? And how this is done usually, or how this is done it has been done before, is using tractography. So this is, oh, you can't really, can you see my cursor? I'm not sure. Oh, also, guys, if you have any questions, like if something is unclear, just pop like in, just unmute yourself and just ask the question. I think that's easier for you to follow and for me to just like, clarify everything on the go. So if you can see my cursor, this thing here is not my plant that hasn't been watered for 3 weeks, but that's a reconstructed tract, so from tractography. And that's how basically those disconnectivity maps, the disconnectomes, are computed. So we take, there is a toolbox, it's called the BCB toolkit. Some of you might have used it. So we take basically an average tractogram from 100 healthy participants. That's important. So we have healthy participants because the tracts, they are similar, but they don't like, obviously they don't look exactly the same in every person. So we take like an average tractogram, and then we overlay it with the lesion from patient, coming like from a stroke patient in that case. And we look which tracts are basically cut off by that lesion. And that's what we end up with, like those beautiful tractograms, those beautiful disconnectomes that are showing the probability of disconnection for every voxel in the brain. Right, so the probability goes from 0 to 1, from like 0 being not disconnected, so kind of like intact, and then 1 being completely disconnected, or something in between. Okay, so our goal was to take that a little bit further, because so this is great. Oops, sorry, this is great here, but it's not in clinical use, right? So you can basically connect those disconnectivity profiles to certain functional outcomes, but despite the valuable information that you can obtain here, it takes pretty long to compute the disconnectome, and it's not clinically in use at the moment. So that's why we wanted to apply artificial intelligence and check whether we can basically push that to another level. And what we did is we trained a deep learning model, a 3D UNet model. So that means 3D because we use 3D pictures, like all these brain pictures are in 3D, and UNet is just, it's called UNet because of its shape, because it's a U. So that's the architecture of this artificial neural network. And we have, so what those networks can basically do in general is extract meaningful patterns from large amounts of data. And you can imagine that like a 3D image is like each voxel contains basically data, right? So it's a very large amount of data. And that's how basically the UNet is constructed. So we have the encoder on the one side, the decoder on the other side, and like multiple layers of interconnected units. The inputs that we use for this model, so it was all like done in Python. The inputs that we used was a binary lesion mask, so what you just saw on the previous slide, and then a disconnected template. So the template was just, for the model to know, okay, these are the tracts that basically exist. And we trained this entire thing on 1,333 synthetic lesion disconnectome pairs. So the outcome was, no, not the outcome, but like the output, the ground truth that we used for the model to resample was the disconnectome computed by the BCB toolkit, so by the conventional disconnectome in order to train what we wanted, right? So we used 1,333 synthetic lesion disconnectome pairs. Synthetic means that we had basically synthetic lesions that were paired in their size and in the hemisphere with the real lesion, but they were not like they were randomly distributed in the brain because what's the thing with stroke is that stroke doesn't happen just randomly in the brain. So there are like basically some hotspots. And in order to basically cover as much variability as we can and produce as many or as much data that is as variable as possible, we use those synthetic lesion disconnectome pairs. So that was what the model was trained on. And then as validation, we used real lesion disconnectome pairs. All right. And at the end, we wanted to check whether, like, not only whether we can resample those disconnectomes with the deep disco, but also check how they would perform or how they would work in a different framework. And the framework was about predicting neuropsychological scores. So we had like 139 patients. So like, you can imagine, like, we can't really have, maybe there are data sets of like 1,333 patients with like a bunch of neuropsychological scores, but pretty hard to obtain like clinical data. So we had 139 patients who had like over 80 neuropsychological scores on like language and motor and bunch of impairments. And we wanted to see whether we can use deep disco to predict their scores 1 year after they suffered a stroke. But I will go a little bit deeper into that, but that is not our main focus for today. So after all this technical talk, this is probably what you were excited to see. So that was the result back then in our work, that the 3D UNet actually accurately resembles the disconnectome. So the deep disco actually does something. So in the upper row, you can see the BCB disconnectome, so the ground truth that we used, and then the deep disconnectome, so the deep disco, the output of the model that we trained, right? And it's actually visually pretty appealing, right? You can see like everything is captured pretty well. The only thing what you probably might notice is that the deep discos, they're like a little bit smoother and might maybe not capture every voxel and every detail that much. And this is kind of confirmed here as well. So although it's pretty accurately resembled, here you can see basically just the frequency of disconnected voxels. Like, we had 1,333 lesion disconnectome pairs. So you can see that for the BCB toolkit and for the deep disconnectome. And then the deep disconnectome, you can spot that like those main fibers are like super frequently disconnected. They're like all red here, right? Whereas those U-shaped fibers, like those U-shaped association fibers that are a little bit more fine-grained, they are less well captured by the deep discome. But our goal was basically to check, okay, well, we got a pretty cool result here already, but what is the performance of, like, can we basically use the deep disco somehow? And for that, we created this morphospace using a dimensionality reduction algorithm, UMAP. So in essence, you basically just take all those 1,333 deep discos that we had as an output, and you try to reduce their dimensionality to create a 2D space. So here in this 2D latent morphospace, each of those little dots is one of the 1,333 deep discos. And basically creating the space allows, so in that space, you have similar disconnectivity profiles. They're clustered closer together, and disconnectivity profiles that are dissimilar. So they're like, if there's a very, very dissimilar lesion that leads to a dissimilar disconnectivity profile, those patients, those disconnectivity profiles will be further apart in the space. So for example, this one and this one, you can like immediately spot they have a very distinct profiles. So that is the main thing from the UMAP morphospace. And the very cool thing is what it allows us to do is to embed a new patient into that morphospace. So obviously, ideally, we would map like the entire space would be covered by those blue dots. But that's already enough to create, a space that is basically assuming that like how a disconnectivity profile, for example, here in this empty space would look like. So that allows us now, having those 1,333 disconnectome morphospace, that allows us to have a completely new patient, say from Manchester, a stroke patient. You have his delineated lesion, put it in the deep disco, have a deep disco or this deep disconnectome as an output, and then you can embed that new patient into the space. And having now, you remember those slightly over 100 patients with neuropsychological scores? We did that for those people, and we embedded those 139 new patients into the created morphospace and correlated the location where they land with their individual test scores on each of the over 80 test scores that they had. And that actually allowed us to predict or to create a prediction framework to predict test scores for completely newly embedded patients. So that's basically how it works. We have this same morphospace, right? It didn't change from here to here. And let's say we have like the first score, which is like a motor score, okay? And we embed, so we correlate the location of the patients with their different motor scores, and we obtain this kind of heat map that for each score separately, right? That represents a kind of risk area. So you will be able to tell, okay, those people here are, or those stroke patients who land in here, they will have a way higher risk of having a motor impairment compared to, for example, these ones here, right? And then you take another score, let's say score 2, which again, it doesn't change the morphospace itself, but the heat map for score 2, let's say it's a language score, it looks completely different, right? So the risk area, the heat map is located here, meaning that the patients who were previously, for example, not affected by a motor score risk, so not affected by having an impaired motor score, that seems to be like a language hotspot. So those people who, with their disconnectivity profiles, would land into that risk area, they will very likely have a impaired motor language score. So this is what we can basically do and how we can apply those deep discos. And you remember our goal was basically to compare whether the deep discos, the generated AI generated thing that nobody believes into, or at least it has a lot of skepticism in the field, um, whether they perform better or worse in this score, like in this neuropsychological score prediction, and not only like in the visual um, resemblance. So what we found out was that the deep disconnectomes actually outperformed the BCB toolkit, so the conventional disconnectomes. I used to call them boomer discos. But yeah, so that was a pretty surprising result, right? So we checked for all these 80, we had 86 neuropsychological tests ranging from like different motor tests to different language tests and so on. And yeah, so what we found out was that they significantly outperformed the ground truth, the conventional disconnectomes. And we thought like, okay, there must be a mistake. Like it can't be it. Like how can something that is trying to resemble the ground truth actually outperform the ground truth at some point? So we looked into it and started this kind of investigation. And sorry. And for that, we computed Euclidean distances. So we took again our morphospace here, and we computed the Euclidean distances of each point that was like each disconnectome to all the other points in the space. And we obtained this graph. It's a little bit complicated to understand, but I walk you through it. So we have basically close distances. That is like we have on the x-axis the close distances to far distance, right? So close distance means that that it would be like within the cluster. So here that is the close distance, and far distance would be like further apart. Okay, I hope I got you here. If you have any questions, just pop in. I can't see your faces, so that's why I can't read the audience. And you can tell here that the difference here is in the negatives for the close distances, meaning that for close distances for within the clusters, the disconnectomes are further apart. And for far distances, they're closer together. What that means is, so within the cluster, so we look at each individual, cluster they're just like exemplary across the clusters, but we look at each individual cluster, and those points within that cluster that are actually close together, they are now further apart. And those clusters themselves, they're closer together in the deep discomorpho space. What that means, though, is that, or how it probably positively benefited the performance of outcome prediction, is that the segregation between similar patients was improved. So this part here is basically important because patients who have a very similar disconnectivity profile are now segregated better, and patients who have a dissimilar connectivity profile, they are segregated worse, but it doesn't make such a difference, or it doesn't affect it negatively, because their disconnectivity profiles, if they're like clustered already further apart, they are already so different that it doesn't really matter, because like they will have such a different disconnectivity profile that it doesn't matter for the prediction, because that can already keep them apart. But what matters is to model those like very slight differences within the same assessment. Right, so this is like just wrapped up on the on what's like on the background of the deep disco. So what we can tell as a little summary is that the 3D UNet accurately resembles statistical maps filtering normative white matter networks, and that all happens 720 times faster than with the conventional disconnectomes. And the deep discos also significantly outperformed the conventional discos. As I just showed you, it was for a long-term stroke outcome prediction. That was like long-term means 1 year. And that all showcase basically that AI-driven models may enhance the efficiency for in clinical settings. And you can all find the, sorry. You can also find all the information related to that in the publication in Brain Communications, which was, I think, last year or the year before. So yeah, but now um, we also, I'm gonna take a sip before we try it together. Mm, so in order to make it a little bit more accessible, especially for the clinic where it's not used yet, right? But it should be. I created this GUI that we actually gonna test out together today. And in the GUI, you first, so there is a link. Sorry. There is a link. We can also go like through the installation together in a second, but I'll first like walk you through what you're gonna see. Um, so once you install everything and once you install the dependencies and sorry, once you install all the dependencies and the virtual environment, and launch the Deep-Disconnectome, you'll see a window popping up that allows you to select a model. So the models that are up for selection, it's for the association fibers, for projection fibers, commissural fibers, and the whole brain. I also tried to like with Paint or like some other software, I was trying to indicate what they are, but some of you may know association fibers are the fibers in the cortex connecting like different parts of the cortex. Projection fibers are connecting the cortex with other areas in the CNS, such as like the brainstem or the cerebellum. Sorry. Commissural fibers are the fibers connecting the two hemispheres, and the whole brain model is basically all the fibers in the entire brain. So these are 4 different models that we trained. It's all Deep-Disconnectome, so it's all the same architecture that we were talking about before with the 3D UNet. But so the whole brain is just giving you the entire Deep-Disco, and the specific models, like the specific fiber models, are specialized on like specific fiber groups. So upon the selection of the model, the like next window opens where you can like, I guess it's very I hope it's very self-explanatory. So you see your selected model. You can load either a lesion mask or entirely like a whole lesion mask directory. The important thing here is that the lesions, as well as, well, all the lesions in the directory and the lesions, they must be in MNI 2 mm space. So MNI space 2 mm, because the model was trained that way. And I have not implemented yet a automatic like converter or resampler that is also sorry, that is something that's on the way. But for now, you have to convert basically if you have a lesion in another space or with a different resolution, you gotta convert it yourself before being able to calculate the Deep-Discos. So basically, you can load here the mask or a mask directory. You can select an output directory. If you don't select one, that's not an issue, but they will all land in the same directory as where you got them from, basically, like where the lesion mask or where they were. And basically then you can click on generate Deep-Disconnectomes and it's okay, let's go. And once you generate it it's pretty quick as well, like it happens within seconds. You obtain a Nifty file in the same directory or in your output directory based on the model that you selected. So it will be named after that as well. And then you can just proceed and, for example, change the model from projection, for example, to commissural fibers. And so this is how the output that you get would look like. So this is, for example, the input lesion. Ignore the brain template in the background. It's just like for you guys to see it a little bit better and to to have a better overview of like what kind of fibers these are. So basically we got the input lesion, which is just this red marked binary lesion mask. And then we have here are the four different models, like the outputs for that lesion mask of the four different models. And can someone name like can someone because we had this little recap just earlier on like different fiber groups. Can someone say what kind of from which kind of model that the first one might have come? Hear anything? Okay, so we see that we have the cortical connections, right? And some like CNS connections, I guess. Okay. So this is the projection fibers model, right? Someone an idea what kind of fibers these are? So we have fibers connecting, we have fibers going from one hemisphere to another. So these are maybe the chat. The chat is I can't open the chat. Maybe commissural fibers. Very good. If somebody guessed it in the chat, I'm proud of you. Um, okay, the third one, that one, this looks like, it captures a lot. It captures like kind of all the connections, all stuff that there is. Of course, it's a whole brain model. And then we got the last one, which is the association fiber model. So you can see, all the cortical connections here. So this is basically how it looks like on my screenshot in 2D. But this would be like how it looks like in 3D. I just chose the example of the commissural fiber. So same input lesion. Things like you're gonna have that also. You have access to this one as well once you download. Yeah, once we get into the downloading part, and then can try it out together. So basically, this is just an example of the commercial fibers. And oops. So if you open it in FSL, then sorry. So I usually use FSL for that, but you can also use like ITK Snap or whatever you prefer. If you open it in FSL, then you have the opportunity to also load an Atlas overlay, right? And this is the extract HCP probabilistic tract atlas, which is already integrated in FSL. So you could basically load that one, which is pretty cool because if you then load the deep disco output. So this is the commercial deep disco output that we just had in 3D, right? And looked into. And you basically overlay it with the tract atlas. Then you can just like play around a little bit and check out, okay, which fibers are actually disconnected. So you might have your lesion, and God knows, like if nobody knows all the fibers, nobody knows all the fibers, so I'm taking that back. But like it's hard. It's hard to sometimes to distinguish those fibers, right? If you haven't been looking on them for 20 years already in your research time. So that's a pretty cool help having like an atlas, and this atlas not only shows you basically here the percentage. So if you move, your cursor to the voxel, it just shows you the percentage of the of a certain fiber, white matter tract. So 79% of forceps minor, for example, here. And then you can just like move around here and check the fiber that might be, that might be disconnected. You can also just load the basically well, not color the tract so you can more freely probably check your deep disco output. And there's the other cool option in FSL that's once you, for example, identify here the forceps major and you're like not completely sure because of the colorway or like the random coloring, then you can also just click show and hide and just see the entire tract and how it is looking like. So that is pretty cool. Yeah, that is like a little input from my side, I would suggest I can well, I will continue sharing my screen and I will just go to the folder I just shared with Ashley, or like probably you guys have it in the chat, and go and like do all the stuff that I just talked about basically on my screen so you can follow it. Does that sound like a good idea? Okay, cool. I will then stop sharing quickly and share my entire, very unprofessionally, I will share my entire desktop now. So I really hope that there's like nothing, nothing embarrassing happening. Okay, cool. Um, all right. So we have this is basically, it's called differently for you. I think I called it Deep Disco GUI, but it's exactly the same folder. I'm gonna delete the virtual environment. So that is the folder that you'll be able to download on Dropbox, and that's the content. So as I said, it runs on Linux and on Mac and on Windows. So depending now on which operating system you're using, you're gonna have to click, like I was trying to make it work so that it just works with a double click. But if it doesn't, then let me know. I will try to help. Maybe I'll just open the chat also in a second. Um, so if you're using a Mac, then you just click on Deep Disco. I think it's called Deep Disco Command or something. It might have an ending, it might not have an ending, but like it's just Deep Disco or Deep Disco Command. If you're using Windows, then you click on deepdisco.bat. And if you're using a Linux operator, then you click on deepdisco.desktop. All right. And in case, if you're using a Linux and in case it doesn't work, then so there is this one file, a txt file, it's called Linux execute. It gives you, it basically says, yes, trust that, and allows you to execute it. So you just like copy this thing and paste it into terminal and run, and then you should be able to double click that. So in case that doesn't work. Okay, I am on the back. So I will just click Deep Disco. It will open my terminal and then it will start setting up the environment, right? This is happening only once, so it takes a while, but it happens only once. So it installs like all the packages. You might also not see the image, right? So that was unless you're using a Mac, I haven't tried that yet, and probably it won't stay in the last version because my supervisors won't allow me to put all the stuff yeah in the final versions of the software. But as long as it's still on its way and we're still creating it, it has a little fun component to it. Okay, so this means all the dependencies are installed and now we can launch the Deep Disco. So we click on launch and it might take a while. If it doesn't open after like 3 seconds or so, then you can just terminate a running process. Probably not so good, but you can terminate that and just like click on Deep Disco again, and then it should be able to launch the first window that I showed you also during the presentation. So I'll just wait a second. And if somebody has any questions meanwhile, or runs into any issues with the installation, also, for example, on Windows, if you run the bat command and you start installing it, and it says like update pip or something, then keyboard interrupt everything and update the pip, because otherwise it will probably or like likely run into get stuck or run into a loop or something. So updated pip is yeah is recommended. Okay, hey, here it opens. So we have this little cool icon of the Deep Disco, which I'm very proud of. And you can't close the terminal since it runs in Python. So I will just hide the terminal, and I won't hide the folder that you all probably have in front of you now as well, in case you were able to access the Dropbox. So here we can now select something, right? So let's, I don't know, let's select the commercial fiber model, right? So this opens up the deep disco surface that you also just saw during the presentation. We can load a lesion mask, and I have in the folder, in the same folder, I have example lesions there that are in 2mm MNI space, the ones that you need. There are 4 example lesions, so you can just, play around with them. I'll select lesion 1. I open it. You see here your selected model is commercial fibers. The loaded lesion is example 1. I will not select an output directory because it's just going to put it in my example lesion folder. And then I click generate Deep-Disconnectome. And I hope it doesn't crash now because okay, cool. So the Deep-Disconnectomes were successfully generated. And now you'll see here the path where it was saved and as what it was saved. So it's in the example lesions in the same folder where I just got it from because I didn't select an output folder. That is not good practice. You should not do that. Select, create an output folder where you have your outputs. Otherwise, yeah, you might get confused at some point. And the Nifty file is called example1 deep disco commercial fibers because that was the model that we selected. Now we can, for example, also change the model. Now let's say we're interested in looking at the cessation fibers. So we select cessation fibers. Again, we load the example1, and we can again click on generate Deep-Disconnectome, and then it generates the cessation fiber one. So that is pretty much it. Now we can open FSLIze as or fossilize, whatever you prefer, as they call it, because the logo is a little fossil, so I guess it's fossilize. Anyone who knows, feel free to correct me on that. And so I just loaded the template. You don't need to load that template. It's in a different orientation, basically. I think it's different. I don't think it's 2mm voxels either, but I like the template. You can just if you don't have any other template, if you have FSLIs on your computer installed, then you can load I think it's here file add standard, and then you can load basically from any standard MNI. Well, you can load any MNI thing in here. So you have basically a background. And all right. So we go back to our example lesions folder where we just got the output of the deep disco, right? So we had example1 commercial fibers. So we put it in here. You can change the colors. I put it on hot. And you see the output of the deep disco in your FSL eyes. And from here, as explained, you can, I think it's going on ortho view, and then atlases. For me, it's already activated, already checked. So I have all the atlases. Maybe I should make it bigger so that you can see actually my entire screen. It might be smaller otherwise. So here you can basically select the extract HCP atlas, and this will then look something like that. So that's also familiar, right? That you just saw in the presentation. Up here where there's this black little dot, you can just click the dot, and then you'll see just the outlines. And you can also change the width of the outlines. Yeah. So this is where you can see, all the tracts. And what I was talking about earlier as well is, so you basically get your cursor to a certain voxel, and here it says underneath, where your extract probabilistic tract atlas is selected, it shows also the probability of the tract that you just that you're on with your cursor. And you can either press show or hide, show or hide. If I press show, Then it shows it in the same colorway that I chose. So I don't want to have that, but I just choose some other colorway, and it shows the tracked the forceps minor completely. So I can also just hide the atlas and check, okay, wow, this is my deep disco. Oops, sorry for that. Um, this was not supposed to happen. And oh yeah, my FSL just oh, okay. That is some you sorry, I can't get out of the Zoom thing here. Okay, never mind. We need now we got rid of the sagittal view. However, doesn't doesn't matter because we're more interested in the horizontal one here, where we can beautifully see the forceps major and basically also check how much it overlaps with our disconnection. So yeah, you can just play around with that a little bit. What you can also do, not with the deep disco though, but with the conventional disco, is the computation of the neuropsychological scores. So we have the disconnectome symptom discoverer, the DSD for that, and invented by Leah Talozzi. There is a publication in Brain about it, which is the framework that I use for the neuropsychological score prediction. And here you can basically select, like, these are all the functions. She trained on the same data sets as me. So we used exactly the same patients, exactly the same data sets, where the deep disco outperformed the conventional disco. But that's pretty cool that you can basically select like motor functions, language, visual, spatial attention, or like verbal memory, pain, sickness, blah, blah. So let's say we want to calculate the scores of language or a specific disconnectivity profile. So here it says exactly the same thing. So it's the same for the deep disco, right? So you have to have the disconnectome in MNI 2 millimeter space and in Nifty format. And you choose a file which is either, yeah, it's a disconnectome. Oh my gosh, it's like my download folder now. That is going to be shown on the entire internet. I do not. Where is my disconnectome? You can download also, like, just to play around with it. You can just like download patient disconnectome example. So we'll have it. It's insecure file. Great. We'll have it here. I'll just put it on my desktop, and then you can proceed, choose file from the desktop, disconnectome, open it, and run the thing. And at the end, like, it just takes like a fragment of a second basically. And at the end, you will have, here it is. So you'll have the coordinates of the UMAP, right? So you'll have a similar UMAP that's what I computed with the deep discos. Basically, you'll have the coordinates where that specific disconnectome that you just uploaded would fall into, right? And then the language scores. And they're pretty, like, that's also not just a range of scores or like a classification of like poor outcome or great outcome, whatever. It's a prediction of a precise score, which is pretty cool. And we're gonna extend the deep disco to that as well. Now, I have talked so much and I haven't looked into the chat at all. So I will probably just stop my screen share and take your questions or assist with, if you've been following and you've been doing the whole thing as well, then I will just try to help as much as I can. But yeah, thank you everyone for listening and for hopefully getting it done as well, and for having me.
Thank you so much, Anna. There are a couple of questions in the chat that are popping up within.
I see. Yeah.
Did I also miss the reference that you called it a boomer
Yeah.
disco? I love it.
Yes, I did. I did. It was at some point. It was a insider joke between Michelle, who invented the real disconnectome, the PCB toolkit, right? And my youngster AI tool disconnectome. And at some point, I was like, yeah, the boomer version. Um, but she started calling it the same thing, so it wasn't offensive.
I love
Okay,
it.
so you guys can't execute it because you don't have executive rights. So there is this pretty easy command usually that you can just it's like cmod minus xm or something. So you navigate into the folder in your terminal, and then I think it's in the same. Let me check. Mhm. Okay, so it's supposed to be this for cmod.plus deep disco and then command. I guess you could try with that one. It gives you like it adds basically the right to execute. Yeah, I'm sorry for that. It's in an early stage still.
Sid, I think, has raised their hand. Feel free to unmute and ask away, Sid, if you'd like to
Yeah,
share.
hi. Uh,
Hi.
Hannah, wonderful to hear about all this beautiful deep learning stuff to do disconnections. I can already think of potential clinical applications. Uh, but I guess I'm stuck in the first stage to get it to open.
Oh,
So I'm
sorry.
on a Windows right now. I mean, I have access to
Yes.
Linux too, but I haven't moved this over while we are on this. So I'm on a Windows desktop. So I
Mhm.
clicked on Deep Disco, the Windows batch file, and nothing shows up. So has
Okay,
it that
so
been
for that,
tested?
yeah, so have you downloaded it from the Dropbox?
Yeah.
Okay, perfect. So you navigate into the folder,
Okay.
right? And then you just run. So I think in Windows it's run or execute and then yeah, run or actually, you know what? You can do probably Python, like the command Python, just type in Python and then deepdisco.bat. Maybe that could work. Or like execute, I'm not sure what it was in Windows. Um, photos. Let me check 1 second. Windows. Um, or you do you click on it with the right click and then run it as an administrator. Maybe that might get it running.
Trying, but it's nothing is popping up.
If you do basically this, so if you go, if you change directories, go to your, like, go to the script itself, you know, like this, and then just like, and run deepdisco.bat. Maybe that will work.
In the meantime, we've had another question in the chat. What type of programs are ideal for analyzing the disconnection maps? Something like Palm in FSL, if the goal is to relate to patient-specific behavioral scores.
So what was the last? Okay, something like Palm and FSL if the goal is to relate to patient-specific behavior scores. Um, so if the goal is to relate to specific behavioral scores of patients, it is you can't just look at the disconnectivity profiles in FSL, right? So you need to have another framework that basically relates like different scores to each other, or like relates the different disconnectivity profiles to different scores. So you cannot analyze it necessarily in FSL. FSL is just visualizing stuff. So you can visualize the disconnectivity profiles and like check them out. But in order to analyze them, we did that in Python, basically, all of it. But at the end, I was showing the disconnectome symptom discoverer, and there you can actually get the real scores. So you can really just insert your disconnectome and get not only the location of where it lands in the morphospace, but also the very specific scores. So yeah. And if you're interested, like if you want to do that, if you have a big data set, for example, with like over 1,000 disconnectomes, you can and you want to create your own morphospace, for example, right? That could also be an option. Then it's UMAP. So it's the uniform manifold approximation projection. That is the abbreviation. It's like it's this framework, or like it's the algorithm that reduces dimensions. So that's how we can basically insert all the deep discos or discos into UMAP, and UMAP will place them accordingly, like together, the ones that belong together. So basically cluster the ones that are similar together and cluster the ones that are the similar apart. You can do it like with every other data as well. It doesn't need to be, disconnectums. It can also be any other high dimensional data that you want to bring to a lower dimensional space, because that is actually your starting point where you can then do like pretty simple correlations, just like with the space and like a score that we did at some point, and apply like multiple regression. So it was pretty straightforward from there, where we had the morphospace, where we could basically map different profiles in 2D, right? We could basically separate and cluster them apart, and like have some that are together. So we had like some kind of pattern in there, and like some kind of sense in this whole organization. And from there, we just like correlated basically the ones that had neuropsychological scores. We correlated the scores with their location, obtained those heat maps that I was showing, right? And got basically the three main PCA components that were explaining the most variance, and inserted them in the multiple regression, which is like, it's like psychology first year stuff. So it's like it's not like super advanced or anything. It's like basic statistics that you can then apply on it. But yeah, it's easier to get the disconnectomes, of any kind, disconnectomes or deep discos, into like reduced dimension, because yeah. I hope that answers the question.
Thank you. If anyone else has questions, feel free to unmute or just pop the question into the chat. And Sid, if you're still running into installation problems, feel free to connect with us and we can connect you with Anna maybe to work out how to install, if that's okay with you.
Yeah, you can also I can stick around afterwards and just like you can share your screen or something. And for Katie, for the Mac,
Yeah, that's helpful. Thank you.
You also probably need to do like the CMOD thing. I'm sorry that okay. So Katie, you want to run this. So again, chmod.x, and then the path where like you just do a right click on the command file, copy the entire path, or just like drag and drop it. That also works. And Mac, drag and drop it onto your terminal after chmod.x. And hopefully it will start downloading.
It still says permission denied for some reason. I feel like I ran into this problem when I downloaded the BCB toolkit as well, and I'm just trying to remember how I worked around it.
Okay.
What I'm going to do is I'm going to try it on my computer, because I'm at home at the minute, so I'm going to try it on my Windows computer at work, because I'm more used to doing like coding on that one, so hopefully that will work.
Okay, yeah, fingers crossed. Otherwise, just like drop me a message, an email,
Thank
whatever.
you so much.
So
Thanks for
I'm
such an
here.
amazing talk as well.
Sorry for all the coughing. I was like at some point, because I got sick yesterday and I was like, I'm running out of water as well. I was like, oh my gosh, I can't really stop now either. Yeah, you're very welcome. Thank you for having me. Thanks for the invite. And yeah, I hope that was like somehow informative in some sense.
It was amazing.
Yeah,
Definitely.
Thank you so much, Anna. And thank you everyone else for attending. We really appreciate everyone showing up for these workshops. Maybe if we come across some simple errors that people run into, we can also share this as like a way for people to troubleshoot if they're trying to install. We can share it with the YouTube.
Yeah, absolutely. I can also like try to, if I see the comment on YouTube or something, just try to respond on that, like if there is a question.
Great.
So happy to do that.